Okay, YouTube, as we continue our exploration of rational functions, we're going to start looking at their graphs. And interestingly, their graphs are going to contain what we call horizontal and vertical asymptotes. And so what the behavior of the graph looks like near those asymptotes, we're going to explore in this video. So in order to do this, we're going to explore the most basic rational function, which we refer to as the reciprocal function. So just like we have our parent function list, f of x, or y, equal 1 over x. This is one of our parent functions that we learn about, and we refer to this as the reciprocal function. Okay, the reciprocal function. Basically, whatever number you plug in, it's going to spit out the reciprocal, or 1 over that number. So when we look at its graph, let's go ahead and take a look at this. I went in and I graphed in Desmos here, f of x equals 1 over x. And if we make a table here, I'm sure that I can do this. We'll put in some f of x values here. We can see that the graph here looks like this right here, and this is all one complete graph, but we say it has two branches on it. And in terms of the table of values here, the first one I want you to notice here is when you plug in 0, we get an undefined spot, 1 divided by 0. So looking at where x equals 0, we can see the spot on our graph where coming in from the right side of 0, we can see that our graph's y values are just getting bigger and bigger and bigger and bigger and bigger, and they increase without bound. And coming in from the left side, our y values are decreasing without bound, or getting really, really small. Okay. As we look at, say, 1 divided by 1, we get 1, but 1 divided by 2, we get 1 over 2, which is a half. If I were to divide 1 divided by 3, then I would get a third. 1 divided by 4, I get a fourth. What we see here is this. The bigger our x values are getting, then the smaller and smaller the overall value of the y value is becoming. So we get this graph here that on either side seems to be getting really, really, really close to a y value of 0. But only because we're taking 1 divided by a number that's getting bigger and bigger. The overall value is going to get smaller and smaller. So the behavior of our graph here, these two branches, how they get really close to a height of 0 out on the ends, and how they increase without bound or decrease without bound as they get really close to this value 0 here, which was an undefined value. That's what I want to explore in this video. So when we look at the reciprocal function, what you're seeing here are tables of values. And we're going to look at the behavior of our y values here on our graph. Now, we already know that our graph, by the way, here looks like this. So what you're seeing in this diagram are just pieces of it. But let's look at this. We say, let's look at the behavior of f near the excluded value of 0. So we know that 0, we can't plug 0 into this function. We said it'd be undefined. So when we look at really close to an x value of 0 here, we look at as we come into left from the left, 0 from the left, as we plug in x values that are getting really, really, really close to 0 from the left side, we observe that our y values are decreasing without bound. We can see that in the table here. -1, we're at a height of -1. But -1/2, now we're at a height of -2. -1/10, we're at a height of -10. This number is going to keep growing without bound in a negative sense. So what we're going to get used to in this video is what we call arrow notation. And arrow notation essentially just says the same thing we said out loud. It says as x gets really close to 0 from the left. Now, what we're going to do is we're going to make a note here. This is a superscript. And this superscript tells what direction we are approaching the x value from, approaching this x value from. So what we're saying here is as x approaches 0 from the left, we say as x approaches 0 from the left, that's how we'd read it here. We say our y values, we notice we're decreasing without bound, so our y values are approaching -infinity, okay? So we say as we come in from the left side, our y values are approaching -infinity. As we come in from the right side of 0, as x approaches 0 from the right side, we can see that as our y values or our x values are getting smaller and smaller, our y values are increasing without bound. So we say our y values are approaching positive infinity in here. And you notice I don't have to write a positive infinity. If you don't write a positive in front of the infinity, we assume by default it's infinity. So as we come into x values from the right side of 0, we see our y values are increasing without bound, okay? So we say that this is indicative of a behavior of a vertical asymptote, okay? So one thing I want to make sure we write on this graph right here is this. Our parent function of y equals 1 over x, and I really apologize for the quality of that asymptote right there. We're going to write a little line right here. We say x equals 0, and we say it has a vertical asymptote. asymptote, asymptote, at x equals 0. And I'm going to put a little note here. This is an undefined x value. We get vertical asymptotes at undefined x values. So now another thing we commented on in the nature of this graph, we saw that out on the ends, as our x values are getting very big, as our x values approach either positive infinity or negative infinity, we can see our y values are getting really, really close to a y value of 0. That is to say that we said the bigger the number we plug in, like 1, 10, 100, 1,000, our reciprocals are getting smaller and smaller. 1, 1/10, 1 100th, 1 1,000th. So we say it appears that as x increases or decreases without bound, the function y values here, the y values are getting closer to 0. So in arrow notation, how we're going to read this is as x is getting really close to positive infinity, as we go to the right side of the graph, positive infinity on our x values, our y values are getting really, really close to 0. And as we do this, we go x values that we're plugging in are approaching negative infinity. As we go to the left, we'd see that our y values are also getting really close to 0. So we're going to say that this graph of 1 over x has what we refer to as a horizontal asymptote. And so a horizontal asymptote here is at y equals 0. And I'm going to say that on this particular graph, it has a horizontal asymptote there. So our y values approach 0 as our x values get really big. So in terms of arrow notation, and this is kind of how I want to leave this video off, we say arrow notation. Let's get used to reading these things here, but we say as x goes to a or x goes to a from the right or from the left, we'll see the superscript. So as a superscript here, we'd say as a approach, as we approach x values from the right of a, we're saying as we come in from the right side of that x value, what are our y values doing? And as we come in from the left side of that x value. Now, as x goes to infinity or negative infinity, we say as x approaches infinity, this is another way of saying as we go way far out to the right, and as x goes to negative infinity, this is way far out to the left. Cheers.